Welcome to the lecture of CRE-1. In the last few lectures, we were talking about the designing of a reactor. In the first lecture, we had already discussed about the performance equation of a batch reactor. And in the last lecture, we had talked about the performance equation about the CSTR, means continuous stirred tank reactor or a mixed flow reactor. A mixed flow reactor, which is also known as a back mixing reactor. Today we are going to talk about the another continuous flow reactor, which is plug flow reactor. And remember, we are talking about it at steady state condition. Steady state. That means the parameter will not change with respect to t, but it can change with respect to coordinate x, y and z. So you need to remember it because in MFR or in a batch reactor this was not the case. In those reactor the parameters are also not changing with respect to coordinate, but the plug flow reactor it will change with respect to coordinate, because basically plug flow reactor it is nothing but it is a straight tube in which the reactant is flowing from one place to another place, and the concentration will gradually reduce throughout the length. So that's why the concentration is different at every coordinate. So because of that, we will say that the concentration and all other parameters are the function of a coordinate x, y and z, and it is at a steady state. But over here plug flow reactor is a tubular, so we will take the coordinates of r, theta and z instead of x, y, z. R, theta and z are the cylindrical coordinates and x, y, z are Cartesian coordinates. Now our first step is to make a material balance over the reactor, but before that we need to think about the making material balance, because there is two way. First way is that first of all we can make the material balance on entire reactor, and second way is that we can take some small piece out of the reactor, circular small piece, and then make a material balance over it, and after that we will make the integration for entire reactor. Obviously the second method is more useful, because over here the parameters are changing with respect to coordinates, and because of that we need to use the integration. So we will make the material balance over the small piece first. It is also known as a cell balance in the fluid mechanics, so it is a kind of a cell balance over here. As you can see over here, this is the figure of a PFR. We are taking a small cell over here which has a volume of a dV, and the length is a dl. Over here the inlet flow of a material is a Fa, and the outlet flow is a F plus dFA, and the changes which occurs in the form of a conversion is a dXA. The entire inlet flow is C anode concentration with zero conversion, and in the last when material goes out, the final concentration of A is a CAF and the final conversion is a XAF. The volumetric flow rate is also a VF. So now we will make the material balance over this small piece. So as you know that general material balance equation is in plus generation is equal to out plus accumulation plus consumption. Now over here We are talking with respect to reactant, that's why the generation term will get cancelled out. So and our consumption term will stay over here. Then accumulation term is also will get cancelled out because over here this is the continuous flow of a reactant, so that's why there is no accumulation within the reactor. Now we will replace the in with Fa, out with Fa plus DFA, and consumption with minus Ra, rate of reaction into volume of a reactor. As you can see over here, there is a detailed calculation of this material balance. The Fa will get cancelled out, it will cancel each other, and we can write the DFA is equal to Fa naught into 1 minus Xi. Sorry, DFA is equal to differentiation of Fa naught into 1 minus Xi, and the final DFA is equal to minus Fa naught into dxa, as you can see over here. Then we will put it into equation, and our final equation will something look like this. As you can see that we had integrated the entire equation from conversion 0 to XAF, because conversion 0 is at L is equal to 0 and conversion XAF at L is equal to L. So our final performance equation for PFR is V divided by Fa naught is equal to tau divided by Ca naught is equal to integration of dxa upon minus Ra from 0 to Xa. Over here we will use V by Fa naught when the case is about the CVRS and VVRS, but we cannot partial in between, and we will use tau by Ca naught directly when the case is a CVRS. So now we will see how we can represent the performance equation of a PFR in the form of a graph, and can calculate the volume of a reactor directly from the graph, just like how we had calculated it for the MFR reactor. So basically, first of all, let me write the performance equation over here. V divided by Fa naught is equal to integration from 0 to Xa of dxa upon minus Ra. So our graph will look something like this. Suppose this is our graph. On the y-axis I will write the 1 divided by minus Ra, and on the x-axis the parameter is Xa. Suppose my curve is something like this. The final value of Xa is XAF, and the V by Fa naught quantity will be the area under this curve. Why I am taking the area under this curve? Because in a MFR we had no integration, but in a PFR we had integration. That's why the area under the curve will become our quantity of a V divided by Fa naught. Then we will have the value of a Fa naught from Fa naught divided by Na naught upon T, and from that we can calculate the volume of a PFR reactor. So this is how we will represent the PFR performance equation in the form of a graph. And you need to remember that we can use this graph for CVRS and VVRS both. As you can see over here, this is how they will represent the graph. And as you can see that this is general case we had seen earlier, and it can be represented for CVRS and VVRS both. And this case is the for CVRS because over here we had taken the concentration but not the conversion. Now we will derive the rate expression for the zero order reaction in a PFR. I need you to remember that the rate law does not concern with the type of a reactor. It will remain same for a PFR, MFR batch or semi-batch, any kind of reactor. It will not change with respect to PFR, but a final rate expression will change in every case. So let me write the equation over here. First, tau divided by Ca node is equal to dxa upon minus Ra, but I will replace the minus Ra with K because right now I am talking about the zero order homogeneous reaction in a case of a CVRS, and my integration is from 0 to XAF. Sorry for disturbance, but then after the calculation my final rate expression for zero order homogeneous reaction will something look like this. You don't need to mug up it, just try to derive it on your home because it is very important. Now then I will talk about the first order irreversible but VVRS. That means my volume is changing over here, and my final rate expression is this. Then just like that I will talk about the second order, and there is a rate expression given over here for the second order as well. Now there is few remarks which I want you to remember or take care. For a system of a constant density, that means a CVRS, the performance equations are identical for plug flow and batch flow. So that's why from that we can say that the space time and the residence time for the both reactors are equal, and it can be used interchangeably. And but for the CVRS system there is no direct similarity between the PFR and MFR reactor. It will be different for both reactor, so we cannot use the performance equation interchangeably over there. Now over here there are few examples for the PFR and MFR reactor. I want you to carry out it or at your home because it is very important, and it will help you to gain the thorough understanding in the performance equation for every reactor. In the next lecture we will talk about the comparison between the volume of a PFR and MFR for the different order, and for CVRS and VVRS reactor. We are ending our session over here. Thank you.